Hi, welcome to the Lower Columbia chapter of the Ice Age Floods Institute. This is our July 16th meeting, and tonight we are having Dr. Victor Baker, and he is coming to us from the University of Arizona. He is one of the, I think the foremost, actually, not just one of, authorities on the Ice Age floods, and he's going to be talking about megaflood science. So I am going to turn it over to him, and
okay.
Let's see.
So, yeah, my name is Vic Baker. I have been studying big floods for quite a long time. I started getting interested in the Channel Scabland region around 8th grade when I lived in Bothell, Washington. But I've talked before about the whole story of the Channeled Scabland and J. Harlan Bretts, but I'm going to talk about a much bigger subject tonight. And it relates to Bretts, so I'll begin that way. But I'm going to talk about three issues. One is global, which is the whole planet. The second is megaflood. Megaflood is a word that had been around, but I started using it a couple of decades ago, and it's sort of taken off in the literature to some degree. For one thing about megafloods, there have been no megafloods in recent history. So it is a thing that we can only study by looking at the effects from the past. I'll get into what megafloods are a little bit later. And then the third aspect is science. And this is actually a very timely concern because we see in the news today the word science bandied about. I just heard it in a news conference yesterday about, I forget exactly the context. But the way it gets used is really quite disturbing to me as a scientist, because it gets used as though science is a bunch of facts and truths and things that we already know. And as a scientist, I'm really upset about that, because that's not what I do. I'm not someone that really is that interested in saying all the stuff that is known. I want to deal with things we don't know. And the hallmark of being a scientist is total curiosity about what we don't know and not being satisfied with that, to continually try to figure things out. And the other aspect of it is total honesty in that process. It's perfectly appropriate for a scientist to make mistakes, but the scientist is always learning from those mistakes and trying to do the best they can to represent reality. So tonight we're going to talk about the reality of really big floods. And let's see if I get this to, okay, so the next slide is a depiction of 140 ancient societies. You can see they are around the world. And all of these are some of the societies that have flood stories in their cultural past. Almost all human societies have some story, and these are societies going back to time before writing, to oral traditions. They have stories about giant floods, and they're stories about floods that to them covered the entire world. So these aren't just floods in their backyard. To them, these floods were everything. And people all over the world have these stories. Now, they're often called myths, but this was before science. And these stories were the way that people tried to understand the world. And of course, that's what we do as science. In science, we try to understand that in a honest and curious way. Now, of course, for us in Western society, from Judeo-Christian tradition, the flood that is almost in everybody's imagination and also in religion is the Noachian debacle. And when science was emerging in the 17th century, which is often called the sort of time period where a lot of science developed, this was very prominent. And it had an element to it that separated it from what I said about science. Because if we take the Noachian debacle as the origin of things, then we're saying in advance how things came about. And as I said before, that's not what science does. Science is if you already know the answer, there is no science to do. You already know the answer, there's nothing to study. You just have the answer. Science is about always trying to figure out the answer. And it's interesting how this developed, because the first use of the word geology in the English language, and geology, because there was a Latin word geologia, there was a uses of it in Italian and some other languages. So there's actually kind of a fight among historians as to when it first got used. But there was a book in 1690 called Geologia, a discourse concerning the earth before the deluge being the Noachian debacle. And the guy who wrote it, he had a problem. If you read Genesis very carefully, you will find that there are two sources of the flood. In one story, the flood emerges from the deep, from the fountains of the deep, Genesis 7:11. And in the other story, the flood comes from opening of the windows of heaven and raining 40 days and 40 nights. That's Genesis 7:12. Two stories. Well, in some Christian religion, God is perfect. So there can only be one way it happened, okay? That's, by the way, that's not a science problem, that's a theological problem. Anyway, this fellow Warren chose the first story, and his idea was the giant flood burst from great subterranean caverns. Now, I'm not going to talk too much about that, but in the early days of geology, this idea of a giant flood was actually something that people who did what was emerging as a science of geology, they thought about. And they thought about catastrophes being important in creating the features on the surface of the earth. But this seemed to be in conflict with what I said before, that science is about total curiosity and figuring out the way things happened. So in geology, starting about 100 years later, with a very famous early geologist named James Hutton, the idea came about that if we really wanted to study the planet, and we didn't want to have some statement in advance about how it works, that in other words, we wanted to investigate and figure things out, then we had to just accept that we needed to observe what was going on today, and that we use that to try to understand how things were in the past. Because people are naturally curious, and they see the effects of things. So they try to reason from those effects to their causes. And that's kind of a problem when you're dealing with something that's happened in the past, because we don't have direct access to the past. So for a period of time following Hutton, and particularly for one of his disciples, a guy named Charles Lyell, it was considered unscientific to study great catastrophes because we don't see them happening today. And therefore, there was kind of a bias that developed in the science against the study of big catastrophes. And that bias meant, and this is important, people ignored or didn't understand the evidence of really big, giant floods. That was an opportunity for a particular geologist named J. Harlan Bretz. J. Harlan Bretz, and I knew the guy. I first got in contact with him when I was doing my PhD dissertation in the late 1960s. And he was very helpful to me. He was actually delighted with what I was doing because he had been working on this problem that was contrary to the general way that the other scientists were doing things. And he later revealed that the reason he got into this problem was when he was on the faculty of the University of Washington, which was his first academic job. He was only there a year, but he was an assistant professor, and he noticed a topographic map, the one that is shown on the right. And it was a map of the Quincy quadrangle. The town of Quincy is located to the north of the feature shown on the map, shown as the potholes. Okay, now the potholes is a set of coulees, and this is a picture by Bruce Bjornstad. I think Bruce is in the audience. So it's one of his great pictures. I think this is probably one he got from his drone. It's a remarkable feature because you have this big basin with all these fields on it. It's called the Quincy Basin. And there's no river there. It's just a bunch of flat land, almost flat. And then there is this incredible head cut that looks like a giant waterfall. It even got plunge pools at the base. It's sort of like it appeared out of nowhere. And it is big, really big. You can see the road on the bottom. That's an anomaly. That's something odd. And Bretz, as he tells the story, his colleagues at University of Washington they said, oh, that's not really, don't worry about that. Well, Bretz was a really stubborn guy. And when he was curious about things, he wouldn't let go of them. And this thing kind of stuck in his mind. When he went back to University of Chicago, he got the job of taking out field courses into the Northwestern US. And here he is these were graduate students, and they did surveys in the Columbia Gorge and in the channeled scabland. And here's Bretz on the left here with a pipe, the Smokey the Bear hat. And you notice the grad students all have pipes. They all got hats. And they're all kind of copying the professor here. When he was working initially in the Columbia Gorge, one of the things that fascinated him the most were ice rafted erratics. Now, at the time, it was recognized that these boulders, and these are, I think this bottom one is from Bruce Bjornstad as well, they were also anomalies. You can see the color of the rock is light colored. So these two are light colored rocks. I know the one at the top is a granodiorite, and they contrasted with the general rock type in the area, which is basalt. So, and they were also up at high elevation. So something had to put them there. And Bretz recognized back in the early 1900s with the students that the thing that put them there was ice. The rock could float in the ice and it dropped out of the water. Now, Bretz, I think it was 1909, wrote a paper about that. And here's a diagram from the paper he wrote. He told me that if there was one paper he ever wrote in his entire career that he could erase from the scientific literature and ever have be totally destroyed, it was this one. We scientists make mistakes, and this was a mistake. Bretz inferred that the water that caused this was a sea level rise that brought water into the interior of the Western US. There was a logical reason for thinking this because there were big glaciers up to the north during the last ice age, that was well known, and the mass of glacial ice causes the Earth's crust to be deformed and pushes it down. Therefore, the sea rises and comes in across the land, particularly when the ice retreats and the land is still lowered. So there is an inundation. And that was what Bretz argued here. Well, he later realized that he had the water flow going in the wrong direction. And this is a map he made in a 1925 paper when he figured out, quite surprisingly to himself, but certainly a shock to the geological community, that the flooding was coming not from the ocean into the land, but from the land out to the ocean. So here you have the pattern he recognized before aerial photographs of channelways cut across the basalt of the Columbia Plateau region of eastern Washington, and then through the Wallula Gap, through the Umatilla Basin, through the Columbia Gorge, down to the Portland Delta area, not shown on the map, but also goes out to the sea. So this was his recognition in 1925 of what he called the Spokane flood. And in a series of papers that were quite controversial through the 1920s, Bretz described multiple features through this region. Late in the night, well, actually about 1930, he finally agreed with another geologist who was working in Montana that the likely source of this flood was a large lake that had occurred in the western part of Montana that had been named Glacial Lake Missoula by this other geologist named Joseph Thomas Pardee. So Bretz had a long set of try to thinking where the flood came from, but it was finally recognized in the 1930s that it was Glacial Lake Missoula. But it was still a long time before he could convince other geologists that these particular features of the scabland, which I've described in many other talks, were the result of cataclysmic flooding. In a paper published in 1956, one of the primary forms of evidence that he used that could make his point were the large-scale gravel dunes. He called them giant current ripples, like these on West Bar, that are very large. You can see there's a couple of grain storage towers here. So these things are up to 15 meters high and more than 100 meters in spacing. So they're really big features. They have boulders on the surfaces. So as I said, I knew Bretz. I corresponded with him in the 60s. I interacted with him personally in the 70s. By the way, that's Bretz on the left. That's me with hair on the right. And he was very accommodating in talking about how he did his work. I was fortunate to be able to write the nomination papers for him to get the highest award of the Geological Society of America, the Penrose Medal, which he was able to receive before he died in 1981. My own work on the channeled scabland was basically to show that it was consistent with principles of physics, hydraulics, hydrology, basically all of the quantitative sciences that had developed in the time after Bretz's work. Bretz told me that he was not able to avail himself of those quantitative methods. And what he told me was that when he was young, he wanted to be an astronomer. And he took his first astronomy class and discovered that it had all this mathematics that one had to do. And then he realized that he had fallen out of his bed as a child and hit the side of his head that did mathematics. And as a result, he decided to be a geologist. So that was an opportunity for me. I got to look at relationships like the relationship of velocity to depth. There was evidence in the scablands of the levels of water that were achieved. I could see that features like these giant boulders were completely consistent with the magnitude of this flooding. This is flooding very different than what people, at least in recent time, have ever seen. It is totally beyond what that is. We now have much better quantitative models for looking at these floods. This is it's called a 2D hydraulic model. It's been done by one of my recent PhD students. And you'll see there's a broad similarity. Here's Washington State, here's Oregon, Idaho, and Montana over to the left, or to the right. And you can see that the floodwater, and this is a depiction of water depths, up to 250 meters deep. I mean, this is water, 800 feet deep, is going through the whole pattern. And this is the pattern that Bretz mapped back in 1925. And that fits the topography. So this quantitative model is confirming what Bretz described initially. And of course, we're down here in the beginnings of the Willamette Valley near the Portland Delta. And this was a back-flooded area with fine-grained sediments. The model can also show the timing of the flood. So these are hours, and you can see that by the time the floodwater got to the distal parts of the Willamette Basin, say down by Eugene, it was on the order of 100 hours. It took it about more than 80, 90 hours to get out to the ocean. So different areas were flooded at different times. It took even though this water was moving at many tens of meters per second, it took a while, mainly because of constrictions and backwaters, to make it all the way further downstream. Another thing that these hydraulic models can show is the velocities and power of the water. So wherever the colors are red, it is the highest velocities, more than 20 meters per second. Meters, 3 feet. So this is more than 60 feet in a second. So this is moving really fast. And the velocity of water, as the water goes up, the energy goes up with the square. So you get much greater energy, and that causes tremendous erosion. And you can see how the erosion in places like Wallula Gap and parts of the channeled scabland and the Columbia Gorge, these were all areas where erosion was facilitated. These blue areas where the velocities drop are areas where deposits occur. And those of you familiar with the region know that the area around Walla Walla, the upper Yakima Valley, parts of the Umatilla Basin, the Willamette, these are all areas with fine-grained deposits from the floods. So this hydraulics actually shows how that occurs. So I'll talk about three aspects that kind of take us back to the early part of the science. Remember, we talked about the Noachian debacle. And one of the things that people wondered about that was the magnitude of the event. And I've just said things about the magnitude of the Missoula floods. Another thing people talked about was when this happened, how long ago? And the biblical time scale is on the order of a few thousand years. And then the third one is how that event was global and covered the world. So I'll say a little bit about timescales. In geology, we can look at timescales for things like those ice rafted erratics. So if you have a glacial lake and you've got boulders that have been rafted by ice around that, and you have flooding that has burst out from the margin of the lake, you may leave flood scoured areas, you may leave zones where deposits occurred, you can leave ice rafted erratics on hillsides. The flood eventually goes out to the ocean and you have sediments out on the seafloor. The sediments, as geologists figured out, several hundred years ago, they are telling you about time because the oldest things are deposited first, younger things are deposited on top of that. So the deposits give you a relative sequence of how things happen. Here's an example from the Willamette Valley by a former student of mine who has become one of the important megaflood scientists of the world today, Jim O'Connor, who's with the USGS in Portland. And it's an area just a bit upstream from the Salem in Oregon. And it has deposits that are rhythmically bedded, repeating in their bedding. These are called the Willamette silts. And they have been dated by a technique called radiocarbon between 15 and 12.7 thousand years ago. And in this site, they sit on top of earlier river deposits and gravels. So that's one way the dating is being done. But a newer technique that is coming into a lot of use now actually goes back to those ice rafted erratics. And that is that you can sample the surfaces of the rock and take a measurement of the atoms that are in the surface of that rock and use the particular species of atom to tell you the length of time that that rock has sat on the surface. So at the top, you see some mountains that are in an area Bruce Bjornstad worked with us on. And here's a colleague of mine, Marek Zoreda, who's sampling this. Here's another rock, and these are both granitic type rocks. This one is on Steamboat Rock in the upper part of the Grand Coulee. And these rocks are dated at about 16,000 years ago. The way they're dated is that the boulder was exposed. In the diagram here, you can see where a glacier may have brought a boulder down. The glacier retreats, and then the rock sits out in the open atmosphere. The same thing can happen with an ice rafted erratic. But there's something interesting going on in the universe. So now we're getting to, rocket science here. Supernova explosions that take place way out in the universe produce a thing called a cosmic ray, very high energy particle that hits the Earth all the time. We're being hit by them, Fortunately, not that often because the Earth's magnetic field interferes with that. But when it hits a mineral in a rock and it strikes a particular atom, it changes that to another kind of atom called the cosmogenic nuclide, because of the nucleus is changed. It can only hit the nucleus of the atom. So the length of time that the surface has been exposed to this particular nuclide, fluorine-36, which was what used for the dates I showed in the previous one, builds up with time. So if you can measure the amount of atom in that is of that type, you can tell the age of that surface. And to do that, you need about $1 million, and you get an instrument called a tandem accelerator mass spectrometer. And you rely upon quantum mechanics and nuclear physics to separate out the different isotopes, and you can measure the quantity. Now, I don't have one of these in my lab, so we have to send the samples to other places in the world that can do the analysis. But this technique is now revolutionizing our ability to determine the ages of these phenomena. Okay, so we're getting to the last part, which is the longest. We still have plenty of time, and that is global megafloods. Remember I said Brett's made a mistake with his origin of the erratics. There was another mistake he made, and this is one I think he's pretty happy today he made. Because when he was trying to argue for his Missoula floods, and people were very much against it, he said that, well, maybe this is unique, the circumstances that happened here in Washington, Oregon, this didn't happen other places. So really this idea of common processes we see every day, that's really okay. It works most of the time. He was wrong. We have discovered examples of these kinds of incredible big floods all around the world wherever there were big ice sheets on the planet. And because of that, we have a name for it. They're megafloods. The simple way you can think of a megaflood is these are water discharges, fresh water, mainly, although I'll talk about some saltwater examples. But the flow, which is the volume of water per unit time, is comparable to an ocean current. Ocean currents move a lot of water. They actually have a measure of that named for an oceanographer called a sphere drip. It is 1 million cubic meters of water per second. Now, depending on the size of the flood, that's about 1,000 Mississippi or Columbia River flows. But the thing about megafloods is not that they were just 1,000 times bigger than any river. It's that the water was moving very fast, tens of meters per second. That means the energy levels were hundreds, thousands, tens of thousands of times greater than any of those rivers. That is what made them so spectacular and erosive. That is based principally on physics, and that relates to the other thing I talked about. So Bretz's work and some of the work that was being developed about the time that I started doing science and this stuff in the late 1960s was painting a picture that I talked about earlier. You have this region, the Channel Scab Land, the CS. You had this source area, Glacial Lake Missoula. Interestingly, it doesn't look very big compared to the Channel Scab Land. That's a whole other area I probably don't have time to talk about, but it is one of our current worries in terms of, was there really enough water from Glacial Lake Missoula to do the stuff we see here? We learned in the 60s that there was another big flood that came into this from Glacial Lake Bonneville that was mainly in parts of Utah and Nevada. It came in around the same time frame as the flooding that went through the Channel Scabland. But another thing that emerged is these floods had a huge impact on the floor of the Pacific Basin. In fact, of the area impacted by the flooding, more of it was on the seafloor than was actually on the land. But what came to be emerged starting in the 80s was that this kind of flooding associated with the last ice age was occurring all over the planet. So on this depiction of North America, you see numbered some of the areas of megaflooding, and this little area here with my arrow south of the Cordilleran ice sheet, which is this region here, is the area in the previous diagram. All of this 2,000 kilometers out onto the abyssal plain of the Pacific was the area impacted on the seafloor. And these other areas also had megaflood evidence down the Mississippi and out into the Gulf of Mexico. The biggest in terms of discharge was not Missoula. There was an incredible huge discharge flood in terms of total volume, although it didn't get quite to the peak of Missoula, that occurred about 8,000 years ago as this big ice sheet over Canada broke up, called the Laurentide ice sheet. This put a huge deposit across the North Atlantic. And this one is pretty well documented. There were big floods that occurred in Iceland, and today there are even large-scale floods that can come from the glaciers in Iceland. That's another story. But we have to go all over the Northern Hemisphere to begin to get an idea as to the distribution and magnitude of these giant floods. So now I've turned the globe looking down in such a way that North America is at the top, and the areas in this light blue are the glaciers that covered North America at maximum extent, maybe 18,000 years ago. And these arrows are megaflood directions. The purple are lakes, although the sizes of these lakes varied. They got larger as this big ice sheet, Laurentide, sort of retreated back, and until it broke up in a giant flood about 8,000 years ago. Similarly, in Eurasia, there were giant ice sheets. It used to be thought that the only one was the one that covered Scandinavia. And it was learned more recently that this ice sheet extended much further to the east, and there were giant lakes that were created in front of this ice sheet. Also, the one that covered Scandinavia had streams and lakes, and water was focused around the margin. And something that geologists who were trying to develop these ideas about slow processes on the Earth actually had in their backyard evidence of a giant megaflood that they didn't know about. And it's down here in this place called the English Channel. You had geologists in Britain and France arguing that little floods made landscapes, and they never knew that evidence of an incredible megaflood was right near them. It's as though nature was hiding it. It's not just that nature hid it, the Cold War hid it. The British and the French, of course, were in NATO, and they were worried about the Russian submarines, learning about these deep gashes that were here. The submarines could use those to evade the ships, the sonar and other things that the Allies had. And this pattern of streamlined islands and linear grooves and inner channels was created by catastrophic flooding. It wasn't discovered until the secret data were released in around 2006 by a friend of mine, Sanjeev Gupta, at Imperial College in London. And what happened, this was actually earlier than the Missoula floods. It was in the earlier Pleistocene. You basically had ice sheet that connected Britain to Scandinavia and to rest of Europe. It came across the relatively shallow North Sea. And at that time, there was a ridge that went from France to Britain where the Cretaceous chalk is. And that held in a ice-dammed lake. Ice-dammed on the northern side, but dammed by the ridge on the southwestern side. Well, the water filled up, spilled over the ridge, and it is that flood that contributed to the origin of the English Channel. Now, the area further east in the former Soviet Union, it was impacted by lots of big ice sheets, ice-dammed lakes, and floods. And this area had its own controversial geologist, another guy I had the privilege of knowing, Mikhail Grosswald. He was an employee of the Russian Academy of Sciences, and he was very controversial because he was arguing for these giant ice sheets that initiated out on the ice shelves in the North Sea and then flowed into the land. But he also recognized there were giant lakes. And he had a student, Alexei Rudoy, who Rudoy contacted me in the early 1990s because he had been working on evidence, partly inspired by his advisor for his doctoral dissertation, Grosswald, that this area had been impacted by giant floods. And he, of course, was familiar with my work. This was in the bad old days of the Soviet Union. I went out with him to the field. It was quite a remarkable experience that I don't have time to talk about. But basically, we came to the realization about this phenomena. Unfortunately, this picture reflects off the screen, but here's Rudoy on the right, Grosswald, and myself, losing my hair at this point. And the area we went to, it's called the Gorno-Altai. These are the different regions of modern day Russia. And this is an autonomous region. I'm also going to talk about this area next to it called Tuva. Both of these areas are Turkic people. They live in yurts. You can see that this area is where Mongolia, parts of China, and Kazakhstan, and Siberia all come together. And here's some of the scenery. Here's this whole area that you see in this picture was flooded. Here's a person standing where suspended gravels were carried up onto this hillside. That dot down there is the bus that the person got out of. So you can see the whole valleys were filled with water, just like in the channeled scabland, although the vegetation and everything is different. Here is a giant gravel bar in an area I went to with Rudoy. Here's the Google Earth image of this. There are giant current ripples on this surface, but they don't show up that well. The bar has been breached by this tributary river. You can see from the road, this bar is about 200 meters high. And it's composed of coarse gravel and boulders. The main flood water was going down the channel where the arrow is there. And this was a bar that was deposited to block this tributary valley. This flood had the energy, like the Missoula flood, to move large boulders. This boulder was transported in that flood. In the background, you can see another giant gravel bar. This is a place called Inya, and this bar is a couple of 100 meters high. Floodwater obviously had to be at least more than a couple of 100 meters high. Also, giant gravel dunes, giant gravel ripples. These are even bigger than the ones on West Bar. This is in a place called the Kurai Basin. Here's a picture, and Rudoy is the little red dot there. This is on some of the gravel dunes in Tuva. And you can see how big they are. This is a giant field of gravel dunes. These are the things that Brett's used to convince people about catastrophic floods. There are giant gravel dunes in many places. The world's best are in Tuva. The capital of Tuva is Kazil. If you take a trip there, and it's quite an interesting place to go to, you will see them as you land on the Kazil airport. Not a big tourist spot, but when we got there in 1990, there were Japanese tourists because there is a monument in Kazil. It is the geographical center of Asia. You never know who you're going to meet in the field in Tuva. This guy actually goes there for propaganda films to show what a hero he is, to show how he, is interested in the common people. He gives a watch to a little boy. He's such a nice guy. I got these off the propaganda picture. He wasn't there when I was there, by the way, but he goes there a lot. Okay, so megafloods. We've talked about a number of them. And this is a diagram I did a number of years ago to try to show something about how big they are. These are cross sections of channels that were impacted by megafloods. And the cross sections are exaggerated in the vertical because these channels are very wide. They're many kilometers wide. And the depth, in order to show them properly, I have to exaggerate that. So this little dot here is the Mississippi River. This one here is the biggest channel of the biggest river on Earth, the Amazon. And over here, you can see there are much bigger ones. This is the Altai region in Siberia. And then here's a Missoula flood channel. This one is the Strait of Dover. I mentioned that, English Channel. It's not as deep, but it is very wide. And the numbers on the side show how big the flows were. So the Missoula flood had about 20 million cubic meters per second, 20 sphere drops. And this one is the Strait of Gibraltar. The Strait of Gibraltar was made by a megaflood about 5 million years ago, and its flow was about 60 million cubic meters per second. Now, I don't have time to talk about these. These are on the planet Mars, and that's another story. I will mention the Strait of Gibraltar. So, 5 million years ago, the Mediterranean was a dry basin, kind of like a giant death valley. And it was a basin because the continent of Africa had collided with what is now Europe, and a mountain range was created between this part of Morocco and Spain. It also crumpled up areas in this zone here where the Italian peninsula, Corsica and Sardinia and Sicily are located. So there were two deep basins, one in the Western Mediterranean, one in the Eastern Mediterranean. And the Atlantic Ocean was over here to the west. Well, in the Miocene period, the sea level was rising, and it was able to cut across the mountain range that was connecting Spain and Morocco. And as the water got deeper, it eroded into it, and the full force of the Atlantic Ocean was spilling into the Western Mediterranean basin. Not only that, but as the Western basin filled, then it spilled into the Eastern basin. So big cataracts were created in these areas, and these are now in the submarine topography of the water flows that occurred. This was salt water that was spilling into the formerly dry basin. So here's a little artist depiction of how this occurred. And this, someone asked me about the biggest mega flood on Earth. This is certainly a relatively well-documented candidate for the biggest mega flood. Well, even bigger mega floods, as I said, have occurred on the planet Mars. Mars, in its ancient history, and I'm talking billions of years ago, had a lot of water activity on its surface. Not unlike the Earth. But the interesting thing, excuse me, need a drink of water, is that harking back to the biblical story, remember the 40 days and 40 nights, on Mars, much of this water emerged from the subsurface. In other words, it burst forth from underground. And that is a pretty remarkable thing that we're still trying to figure out. It did so in such quantities that it created a huge water body on the surface of Mars, which was called Oceanus Borealis. It wasn't named by me, but it was named by one of my colleagues. It was a good title for getting our papers published, but anyway, that's another story. Here is a topographic rendition of the northern part of Mars, and the blue colors are low-lying areas. They happen to have been covered by water in the ancient past. And then the red colors are high areas. And you see this pattern here of a giant channel called Kasai Vallis. And this had a source over on the right of the image where these big fractures are, where water emerged from deep underground, flowed in massive quantities into the Northern Plain Basin. And that created a big water body on the surface of the Northern Plains. So I have used my 1 hour. I want to leave one thought as we go back to thinking about this whole story of megafloods. And just think about North America, where we had a giant ice sheet and the Cordilleran ice sheet. We had the channeled scabland. We had the flooding from Lake Bonneville. And then we had a series of floods, very complicated story, related to the retreat of the Laurentide ice sheet, impacting the upper Missouri River, the upper Mississippi, the Ohio River, the Wabash River, the Illinois River, various spillways in Canada. All of these show evidence of mega flooding. And this occurred near the end of the last ice age. Well, there was something else going on near the end of the last ice age in North America. And some of you probably already know what that is. People. There were people coming into North America. And there is a current big controversy of how did these people get there? Remember back to the first slide. There were people all over the world near the end of the last ice age at a time when there were giant megafloods going on. Now, these people didn't have writing. Some of them were just beginning to emerge to the ability to do cave paintings. But if they experienced anything like these giant megafloods, it would have made an impression, at least upon those that survived. And there is no question that it would have been the big story of their existence. And they would have stories about it. And those stories might even persist up through time. Now, this diagram shows scientific controversies about where the people came from that, ultimately got to North America, where they're settled. There's lots of research on this. Some of it involves a lot of dating with the tools I talked about. Some of it involves new genetic studies that tries to relate these people to other people, such as people that lived in Asia or in Europe. But my only point is that this story that J. Harlan Bretz led us to, with his kind of stubborn attachment to the channeled scabland flooding, has gotten to things way beyond what he imagined. And it has certainly been my privilege to be a scientist, to go through that process to get up to this point. So thank you very much. Thank you for the opportunity to talk about my favorite subject of all subjects, really big giant floods. And if you don't have any questions about this, you probably haven't been paying attention. So I think it's up to Sylvia to monitor the questions.
All right. Thank you so very much. That was wonderful. So, yes, you can see all the hand claps there. So on the questions, where have we got the chat? Looks like we've got several. Okay. From from Patty Hyatt to everyone. Now that's a flood. Okay. Vincent Arts, does the slide showing the cross-section of channels show mega flooding events for all those examples? Or is, for example, the Mississippi River cross-section a current non-flood cross-section?
The Mississippi section is a lower Mississippi channel cross-section. So it isn't a mega flood that came down the trough that the Mississippi River sits in. I didn't use that in the slide. I wanted to compare to a modern river channel. The Mississippi and the Amazon are what we call alluvial rivers. They have channels that are sized to the relatively frequent floods that occur in those rivers, like floods that occur every few years. So they are not anything like mega floods. They're a phenomenon that people can observe today. They're the common kind of flooding that occurs. When flooding occurs that goes across the floodplain of the Mississippi, it's relatively shallow, but it may cover pretty huge areas, but it's not very deep.
All right. Ann Backinson asked, how did they calculate the 550 cubic miles of the Missoula flood?
That volume estimate was based on a volume for Glacial Lake Missoula. And the Glacial Lake Missoula is pretty easy to figure out its volume because the ice dam is pretty clear in northern Idaho. And the high water mark of the lake is very well delineated. So you can use the present day topography to just calculate a volume. And that volume, J.T. Pardee calculated it probably as early as the early 1900s at about 500 cubic miles. It's more like, forget the exact number, like more like 2,500 cubic kilometers. But that water had to be released if you had a total emptying of the lake. Now, there's one science problem that we're still trying to cope with, and that is, you remember those diagrams I had of the depth of water through the channeled scabland? If you calculate all those water depths, there's much more water than what could be released from glacial Lake Missoula. Indeed, to just fill the Pasco Basin above Wallula Gap, you have to have something like 1,600 cubic kilometers of water just to do that. And at that time, there was water in other parts of the channeled scabland as well. So one possibility is that there had to be much more water than glacial Lake Missoula. That idea is currently controversial because the only way we could get that extra water would be some way that would be associated with the Cordilleran ice sheet. And the reasonable way to do that would be subglacial water from a subglacial lake. And there is evidence there were subglacial lakes associated with the Cordilleran ice sheet.
Thank you. From Scott Burns, Vic, superb. Do you have a recent publication of that that gives the comparison of the worldwide and Martian megafloods? I love the comparisons.
Well, yeah, the diagram is from a 2001 paper published in Nature. So I mean, I'll send it to you, Scott, but you can also just get it from Nature, the journal. You can go on Google Scholar and put down my name in 2001 and, you know, Mars floods or something, and Nature, you'll get the reference.
All right. Bill Burgle has two questions. Why do the slackwater deposits, say in Lake Lewis, have very little organics or woody debris within their deposits, so more accurate dating can be gained? And then the second is, Vic, what is your candidate megaflood for Noah's flood?
Well, there is not a lot of woody material in flood slackwater deposits like the tushy beds that are associated with what's called glacial Lake Lewis. This has to do with where the water came from. It was basically coming out of a ice age glacial lake. There probably was not forest around this lake. It was probably a paraglacial environment. So it was, if it was vegetation, it was probably tundra. So there wasn't woody material that was at least abundant to get in relative to the quantity of water. The tushy beds do contain shells, and these may have been organisms that were in ponded water between the events that moved in the initial emplacement of the rhythmite units. But there's just not a lot of that kind of organic material. So the shells have been dated, and another former student of mine, Russ Bunker, and I collected some samples from tushy beds at Mabton, Washington, and we got about a 16,000 year date from those shells. So that's another aspect of the dating. One thing we look for with geochronology is a consistency and coherence of many methods converging on the same dates. That gives us confidence, because there's a lot of issues with geochronology in terms of accuracy. So we don't just rely upon a single method or a single date. We, as much as possible, try to use multiple methods that, you know, nature would have to be pretty perverse to trick us if those things didn't converge and actually be telling us something about reality.
He had a second question. What is your candidate megaflood for Noah's flood?
I haven't worked on that issue. I have some friends that have. There's one chain of thought, and this goes to Lamont Observatory geologist who was actually very famous for the studies in the Mediterranean, Bill Ryan. Bill's retired now, but he developed the hypothesis that it was the spilling of the Mediterranean into the basin of the Black Sea. The Black Sea is very weird. The name, the Black Sea, shows that it's weird. It is anoxic. It doesn't have oxygen in the water. And it therefore preserves a lot of stuff. And one thing that was found is that when you go deep into the Black Sea around its margins, there are villages and evidences of people that lived there. And they lived there thousands of years ago. There's also clear evidence that as the Mediterranean rose in sea level after the Ice Age, it spilled through the Bosporus and the Hellespont, the straits near where Istanbul is located. And that salt water spilled into a basin that had fresh water in it, but was much lower. And that would have displaced huge numbers of people who would have sensed that the whole world flooded. And those people would have impressed the people in the areas they went to, which would have included the Fertile Crescent, where now we have Iraq and Syria and those areas. Another hypothesis, and another friend of mine was a proponent of that, was that the present-day Tigris and Euphrates rivers during the last ice age extended way into what's now the Persian Gulf. And the areas of largest human habitation were actually now areas below sea level. Well, that's a very low-lying area. And as the sea level rose again, around 10,000 years ago, water would have spilled across this whole area very rapidly. So again, there would have been a rapid marine invasion of water. And again, that would have created a lot of stories about this. And the people who study the origins of the biblical story and who try to understand this issue of the two sources of water and the like, have all found that the source of that in Genesis was from the time that the ancient Hebrews were in bondage in Babylon, in the Mesopotamia area. And so there has been the scientific work on this, which I haven't been involved with, and I can't really, I've read about it, but I can't pass a particular judgment on it, is that that was a source for the reporting that ultimately came to be part of the Judeo-Christian Bible.
From Peter, conspicuous by your isolation on your world map of megafloods are two in Patagonia. Were those also late Pleistocene in age? Wonderful story, Vic. Thank you. Hey, Vic, your screen, we're starting to only see about from your nose up. There we go.
Okay. I'm kind of relaxing here.
Yeah.
Yeah. Those. I haven't gone to the area, but I have an invitation, and the people who've been working on that are quite intrigued because the main area that is associated with the southern part of the Patagonian ice sheet is along the Baker River. I'm not kidding. That's what it is called. And this area has been recently worked on by a former postdoc of mine, Gerardo Benito, who is one of the world's leader in an area I started a lot of work on called paleo flood hydrology. Gerardo has worked extensively there, and he has a paper that's just come out. There is a book, try to remember the title. I'm an editor, but the main editor is Paul Carling, another megaflood person, and that this volume is coming out under the auspices of Earth Science Reviews. And I can look up the title. It is it is a collection of papers that deals with megaflooding all over the world. And it has a paper in it by Gerardo Benito and others on that particular area. Quite a good paper. The book is called Catastrophic Freshwater Paleoflooding on Earth, A Global Perspective, 2020. It's an Earth Sciences Review special volume. And the papers are published. They are at least online, and there's quite a few of them.
Okay. From Kate Ely, Upper Umatilla River recently experienced a, quote, epic, unquote, flood with a 500-year reoccurrence interval. Evidently, megafloods are valley-forming events. What flow rate or reoccurrence interval is needed to have a valley-forming flow? I don't think this flood was valley-forming, but rather a floodplain enrichment.
Yeah, the terminology that applies to, let's say, 100-year flood, 500-year flood, it's really not applicable to what I'm talking about in megafloods. It's another story. It would be another whole talk. It actually isn't applicable to human understanding because the term 100-year flood has nothing to do with 100 years. And it has nothing to do with a real flood. It is a complete figment of quantitative extrapolation that is used so that insurance companies can figure out rates to charge people for flood insurance. That's it. I'm not joking. That is what it is. Scientifically, it is nonsensical pseudoscience. It's used for engineers to give numbers, to put lines on maps, to tell people where they have to pay for insurance. That isn't science. Remember what I said science is. Science is curious about what the real world is and absolute dedication to the truth of that process. 100-year flood doesn't fit that at all. But as I said, that's another whole story. So you've heard that from a flood person, by the way. You'll get in trouble with engineers, of course. I've been in trouble with them for a long time.
You just busted a myth. Bill Burgle says, was the mega flood that carved the English Channel salt water?
No, it was freshwater. And it was, I did mention it, the water was glacial meltwater, like glacial Lake Missoula. In the last ice age, the water from the Earth's hydrosphere on the surface is mostly in the ocean. And what happens in an ice age is that water is transferred to the land as big ice sheets. So the sea level went down about 120 something, 130 meters. And the area where the channel is today in the North Sea is very shallow. So that was all land. But there was this ridge where the chalk cliffs are at Dover and Calais, and that ridge went across what is now the English Channel today. And that ridge was then carved by the flooding. If some of you saw a recent NOVA program called Killer Floods, there was a description of that process in that film. They had me in it for a little bit of it, but yeah.
Douglas Anderson says, Dr. Baker, it is a treat to finally hear you speak as, whoops, it flipped here. Let me go back to that. It was a treat to finally hear you speak, as I have spent a great deal of time reading your and others' work on the Missoula floods. I was brought up as a Northwest U.S. engineering geology practitioner by Dr. Scott Burns, and on the shoulder of others you have mentioned in your presentation this evening. Please stay well, and thank you for a great presentation. And then,
thank you. I certainly benefited from an engineering geologist who helped me quite a lot early in my career. His name was George Neff, and George worked for the Bureau of Reclamation out of the Ephrata office. And he had done, as he was working on various projects related to the Columbia Basin irrigation scheme, noticed all of the immense catastrophic flood features. And he communicated with Bretts, and he worked with Bretts in the field. And so I benefited a lot from George's experience.
wonderful. And Scott, don't have a last name, but Scott here says, what new kinds of things can be learned from the marine deposits about the Ice Age floods?
Oh, quite a lot, because when the high energy floodwater flows to the ocean, you get something really special that happens. When I was working on the big channels on Mars, remember the picture I had of that giant channel? I had early argued that these were flood channels, that they had been made by water. And one of the criticisms people put at me was, oh, those are channels coming into a water body. There's no delta. Everybody knows when a river comes into the ocean, you have a big delta, the Mississippi River Delta, the Nile Delta, etc. But the people who said that don't know about catastrophic flood channels. They are not rivers. Rivers flow at about 1 meter per second. Very low energy. They move sand. Maybe they move gravel. You saw what Missoula flood moves. That isn't sand and gravel. It has incredible energy. So when it is coming to the ocean, you have water moving tens of meters per second, and it is loaded with big particles or heavy loads of finer particles. When it hits the water, that stuff just nosedives down along the bottom of the sea, the heavy particles. The light particles spread across the surface of the sea as a giant sort of apron. And the heavy particles, they move 2,000 kilometers across the bed of the ocean. So any flood will place a layer of these particles, and the fine ones will settle down on top of that. Well, the ocean doesn't have a lot of other stuff going on. This happens and nothing happens. So these things build up in a stratigraphic sequence. So if we could drive around the bottom of the sea and look at outcrops, it would be fantastic. The trouble is, it's thousands of feet underwater, and it's hard to get there and do field work. So it hasn't been studied a lot. There have been piston cores taken, but for future generations, the whole story of the floods is out there in the sedimentary record in fantastic detail. It just will cost millions and millions of dollars to figure it out. But of course, in science, we don't care how much it costs. We're curious. We'll spend all the money it takes. We got missions going to Mars that cost hundreds of millions that are taking off. And those are great things scientifically, but, you know, it takes money to figure out difficult stuff.
Bill Burgle has another question. Did you take into account the lower gravitational pull on Mars in your megaflood analysis?
Oh yeah, that's really important. From what I was saying about the sediment that moves out into a water body, if you have a lower gravitational acceleration, then the force that is pulling on a particle to get it to drop down to the bed is less than it would be on Earth. So if a particle is moving along in the water at a particular velocity, the force that's going to make it to drop down is less, so it'll continue to move further. The other thing is when you put something in water, there's a buoyancy effect. In other words, there's a resistance to that particle moving down to the bed. As a result, the floods that entered the northern basin of Mars did not just put sediment 2,000 kilometers. The whole northern plains of Mars would easily have been totally blanketed with the sediments from a giant flood. In other words, these would go right across the northern plains of Mars. But there's another interesting part of Mars, and I'm not going to get into this too much, but there were a lot of people that were very critical of the idea of a northern plains ocean on Mars. But we have discovered something really remarkable on Mars that has kind of turned the whole question back to there being a giant ocean. And that is, there were meteors that hit the northern plains ocean, and these made another kind of flooding, mega tsunami. So there were incredible, immense tsunami created that took sediment out of the northern plains of Mars and plastered it up onto the Martian landscape. Now, another evidence of flooding that I had the opportunity to study was the 2011 Tohoku Oki earthquake in Japan. And that had immense tsunami effects. There are places we studied where the run-up heights of the tsunami were 40 meters. And truly remarkable. And that was a tiny thing compared to what happens when you have a bolide impact into an ocean, which is what we have evidence occurred on Mars. If you go back far enough in geological time, the cataclysms are just amazing. We're lucky we're not on the planet too long. We might have a bad time.
Vincent Arts, I believe hope I'm pronouncing that correctly, Vincent, says, Vic, I am an emergency manager and you just blew up my world with your comment on the 100-year floods. I was happy to hear it. You have completely rewired my perspective on my job here in Northern Oregon and along the Columbia River. My question is, since the flood basalts millions of years ago and the mega floods of the Pacific Northwest more recently, why is the Columbia River Channel such a persistent drainage pathway in our region?
Well, of course, one reason for its persistence is it has one of the biggest rivers in the world that's flowing through it. At least it used to flow through it before the dams. So the Columbia is a really big river. And there was a pathway for that river through fairly long periods of geological time. There was a pathway before the floods, entered what's now the Columbia Gorge. The floods obviously modified it, but it was there before. And it was even there when the basalts were in place, because you've got basalt flows that probably originated in the fracture zones in southeastern Washington and even in Idaho that flowed through a predecessor Columbia Gorge and got all the way out to the Pacific Ocean. Cape foul weather, you can walk on Columbia River basalts right on the Oregon seashore, and that they went through the Coast Range in a somewhat different valley, but those had to come through a predecessor Columbia Gorge. So rivers do, over long periods of time, if you have enough time and you have capability of the river, they will carve valleys. The thing that got Bretz in trouble, at least in terms of the thinking of the geologists of his day, was he was saying that the valleys in eastern Washington were too small. The flood spilled out of one valley into another valley. And to his colleagues, this sounded crazy. So much flood water flowing out of one valley into another. But Bretz had the field evidence for it. And he was always frustrated that people would read his papers and dismiss them on a theoretical basis, and they never went out in the field to see the evidence. Excuse me.
All right. Okay. Are there any other questions?
Sylvia, I have one.
All
Yes.
right.
I noticed on the red dots when you had the cultures and the stories and the knowledge of megafloods back over centuries, that Iceland was not visible, yet there were megafloods. Is that because there were no people there?
Iceland, of course, was settled by, the usual story, it was settled by Norse settlers, by Vikings. And this is of particular interest to me because of my Irish heritage. The Norse who got to Iceland in like the year, I don't know, 1000 or so, they found Irish there when they landed. The Irish had actually gone there in the Middle Ages. They were Irish monks, and they were established there. But certainly, the first millennium A.D. was about the time where any people got there. The big floods that I talked about, or that were on the slide, were actually more ancient ones. They were associated with the terminal ice age. But there are big floods that occur in Iceland. They're called Jökulálfs. Jökul for glacier, and Lauf for big burst of water coming out. And those have occurred in human times. So the Iceland people know not to live on what are called Sandur plains. These are the big outwash areas where the floods come. Their farms are not located on those areas. But Iceland doesn't have a lot of people. I think its population is around 400,000, and most of them live in Reykjavik, and so they know about them. They haven't interacted. The biggest one we know of came from Katla, and it occurred around 1900. I don't remember the exact date. And there's argument over just how big it was because it wasn't directly observed. I think one figure is about 600,000 cubic meters per second. So not quite a mega flood. It was short duration. Katla doesn't have a lot of volume of water, but it was able to put this water out really fast because you get with these eruptions, you get a active volcanic structure that is forming within a thick ice sheet. And as the volcanic mass rises, you get a surrounding melt lake. And when that lake gets deep enough, it is because the water is denser than the ice, that water will then form a tunnel under the ice and it'll blow out from the margin of the ice. And if the glacier is thick enough, you can get a water head or depth of water a kilometer or more, and that is the potential energy to drive the flood, because you multiply the mass of that water times the height, the acceleration of gravity. That gives you the energy, and that changes into kinetic energy, which is related to the velocity squared. So that's how that's really where energy for megafloods comes from. You're changing that, and that can occur in an Icelandic, glacial situation with volcanism. And by the way, that mechanism is related to how we think the floods burst out on Mars. But we're not sure that there were glaciers. We think that this had to do with an ice-rich permafrost zone on Mars and volcanism that was underneath this ice-rich permafrost.
Thank you.
Yeah.
Vic, could you comment on the paleontologic finds in North Dakota that have been described variably as
Paleontology in North Dakota. I don't know the context.
they've been described as at the end of the Cretaceous, with the bolide collision
Oh,
and
okay.
possibly a
Okay,
tsunami
so
up the Mississippi.
Chicxulub bolide
Yes.
occurred about terminal Cretaceous Paleocene boundary. And at that time, of course, the bolide hit Yucatan Peninsula. It did create megatsunami features. I'm familiar with the ones that were studied in Texas. And at the time, you had an inland sea that was covering parts of central North America. I don't know the exact geometry in late Cretaceous, but certainly in Cretaceous, you had an inland sea. Now, catastrophic flooding is a great way to preserve fossils because the organisms get swept up in the floodwater and they get buried quickly. I mean, the big problem with animals dying on the surface is other animals come and pick at it and eat it and everything. But if you can bury things quickly and the chemistry is right, then the things get preserved. So not knowing the details of what you're describing, because I'm not familiar with the North Dakota situation, I suspect it may have something to do with what I just said.
Right. So Susan asked, this isn't a question, but thank you very much, Dr. Baker. And I think Sylvia needs to invite you back. Well, very definitely. We've had you a number of times. We always love having you come and present. And we thank you so very, very much. So I think at this time we are going to conclude our meeting. I want to thank everyone for coming. And next month is August. We do not have a meeting in August, but I will be sending out a notice. Our next meeting will actually be September 17th, and that will be Rick Thompson speaking on how the Missoula flood still affects us today. We don't know if that will be Zoom or if we'll be able to be at the Tualatin Library. We'll just have to see how things come out, and we will notify you of that. This meeting, thank you, Dr. Baker, has been recorded, and we will post that on Rick's website gigaflood.com, since our chapter does not have a individual website. It will also be on the Ice Age, IAFI.com website. If you like our meetings, what we present, I would ask you to become a member of the Lower Columbia chapter of the Ice Age Floods Institute. And we thank you again. Thank you again very much, Dr. Baker. We've so enjoyed having you.
Okay,
And
thank you. Thank you for the questions.
thank you. And we definitely will have you back again. Thank